Hey guys, welcome back. It's Mrs. Webb here, and I'm going to spend a little bit of time today talking to you guys about the concept of apparent weight. So we've already been chatting about forced gravity, and we've talked about how forced gravity is really just a measure of the person or the object's mass times the gravitational acceleration that's pulling them toward pulling the object toward the center of the earth. Now that's really what gives us our true weight. So when we stand on a scale, and if it was a Newton scale like the one that we hung up in the classroom, we put our weight on there, and it tells us that we have a weight of let's say 550 newtons. That's giving us our true weight. That's giving us our mass times the acceleration of gravity pulling us toward the earth, right? And that's given by the equation weight is equal to mass times gravity, or for our intents and purposes, we've been talking to or referring to this in terms of our force of gravity. So that's when we talk about true weight. Now, the thing to note about true weight is that the true weight of an object does not change, at least not quickly, right? We may, gain weight or lose weight over time, but it takes some time to do that. So instantaneously, your true weight will not change. It's a constant. But every so often, you may have experienced a situation where you felt really, really light for an instant, or you felt really, really heavy for an instant. And two examples of that are, for example, when most people have probably been in an airplane. When the airplane takes off, there is a moment where you feel like you're really, really heavy, just as the airplane is taking off, right? And what's happening is that your inertia is carrying you forward in a horizontal direction as the plane has been accelerating in that direction. And because of your inertia, your body is resistant to change, right? It's going to continue traveling in that forward direction unless there's an outside force that causes it to change its direction of motion. And so as the plane starts taking off, your body wants to remain on the ground, moving in this forward direction as the plane starts to move in an upward direction. And what you experience is this really heavy feeling because you're pressing into the plane's seat that you're sitting in as the plane is trying to leave the ground, and your body is trying to almost fight that motion of the airplane and trying to remain on the ground because of its inertia. So for an instant there, you feel really, really heavy or like you're being compressed. And then as soon as your inertia is overcome by the plane's upward motion, then you feel that sense of heaviness disappear, right? So that's an example of where it feels instantaneously like you get really heavy or kind of like you're getting smushed or compressed. The flip side is when you feel really, really light for a moment. And typical places where you might have felt this is if you've ever been driving or in a car where you are on a hilly road and you're traveling rather quickly, and as you crest that hill, right, your inertia is carrying you in this upward direction, and then the car starts to accelerate back down the other side of the hill. Well, your inertia is going to keep propelling you in this upward motion. And for an instant, as the car changes direction, the car is going to start leaving you for a brief instant, right? And the seat is going to start leaving your bum until the seat belt takes hold of you and forces you to follow along with the car, right? So for a brief instant, when you feel really light or almost weightless, It's because there's an instant where it's almost like you're about to start floating, but then the seatbelt picks you up and carries you back down. The same thing happens if you've heard of the Vomit Comet. The Vomit Comet is an airplane that is used to train astronauts before they go to space. And essentially what the Vomit Comet does is it climbs really, really high, and then it descends really, really quickly, right? And so the people that are in the airplane have a moment where they actually become weightless because the acceleration of the plane is matching the acceleration of gravity. And so the people in the airplane feel a sense of weightlessness because they're not touching back down on the floor of the airplane or on the seat. So that's what we call apparent weight, and it's a result of an instantaneous change in the rate of motion of the object, right? So the object's inertia is wanting to keep them moving in a certain direction, but there's all of a sudden there's a change in the rate of motion of the object that is going to cause this instantaneous feeling of the object getting heavier or getting lighter. So apparent weight can change. And it changes as a result of an object changing its rate of motion. Whereas true weight won't change, because the true weight is the mass of the object times the gravitational acceleration. And that mass of the object won't change readily. Your mass is your mass, right? So when we have, if we were to have a scale on the seat of our airplane as we're about to take off, what you would notice is that your scale, initially would be reading, however many newtons, let's say 550 newtons. And then as the airplane starts to take off, what you would notice is that the scale would start to spike. It would go to 700 newtons, 800 newtons. And then eventually, once you start moving at the same rate as the airplane, it would come back to 550 newtons. Right? And if you were in an airplane or at the top of a roller coaster and you were sitting on top of a scale, just as the roller coaster crests the top and the roller coaster starts to leave your bum for a brief instant, you would notice that the numbers on the scale would get really light. So they'd go from your 550 newtons and they might go down to 350 newtons. And then as soon as you catch up with the roller coaster, that weight would return to its normal 550 newtons. So what we're seeing when the scale is changing like that is we're seeing the apparent weight, but what we're observing is a change in the force normal or a change in the force tension. So a force normal if we're sitting on a standing scale, a force tension if we have something hanging on one of those hanging weight scales like you would see at the grocery store that you put your produce into, or like the one that we had in class where we hung the mass from the scale. And so I've got a little diagram here for you that I quite like that shows you exactly what we were just saying. So if our elevator is moving up, let's say, at a constant rate, we have an acceleration of 0. Or even if the elevator stopped, it doesn't matter, as long as the elevator is in uniform motion. If the acceleration of the elevator is 0, then the apparent weight of this person standing in the elevator is going to equal their normal weight or their true weight. Okay, so if the acceleration is 0, the apparent weight and the true weight are equal to each other, because the force normal in our free body diagram is equal to the force of gravity, right? So we've got a balanced system. If our elevator is moving upwards, it's accelerating in this upward direction. See the little lines, motion lines down here? So the elevator is moving upwards, maybe it's getting going. It's accelerating in this upward direction. Well, this person's inertia is going to want to keep them where they're at, moving at a uniform rate. And so if the elevator starts to press up on their feet, because the elevator is accelerating this upward direction, the scale is going to sense that they are getting heavier. And what will happen in terms of our free body diagram here, and I'll just draw this here at the bottom, is if this is the person's force gravity, because the floor of the elevator is pushing into their feet, their force normal is going to get really big in comparison to that force of gravity, which means that they're going to feel really heavy. They're going to feel a sense of heaviness, and it's going to appear like their weight is changing. In contrast to when they're at a uniform rate or an acceleration of 0, where their force of gravity is equal and opposite to their force normal. Right? Now, if instead, let's say they get to their floor and they decide they're going to go back down, right? So now here's our little motion lines showing us that we're descending. So for a brief instant, this person is going to want to stay, their inertia is going to want to keep them where they are at. Let's say they're on the 5th floor. Their inertia is going to want to keep them on the 5th floor. And the elevator is going to start to move downward. And for a brief instant, the elevator is going to leave without them, right? The elevator is going to leave without them until this person's gravitational pull sends them down toward the floor of the elevator, right? So for a brief instant, if the elevator leaves without them here at the scale, what that scale is going to measure is that the person is getting lighter. And in terms of our free body diagram, what's going to happen is the person's force normal for a brief instant is going to get really small because they're not really weighing down the scale anymore. That contact force is decreasing. And then the person's force gravity is going to stay constant. The force gravity never changes. Now, if the person's acceleration equals the gravitational acceleration, if the elevator's acceleration equals the gravitational acceleration, well, that's the scenario of the vomit comet. That's a scenario where the elevator is going to be accelerating toward the Earth at a rate of 9.81 meters per second squared. And the person's going to be falling toward the Earth at a rate of 9.81 meters per second squared. And so this person is going to continuously be falling. The elevator is going to be falling at an equal rate. And in terms of the scale, they'll never come back onto the scale because the scale and the person and the elevator, it's all falling at the exact same rate. And that's where we get this feeling of weightlessness in that scenario. Okay, and so at that point, in terms of force, in terms of our free body diagram, basically the only thing we've got left is our force gravity. And our force normal has just completely disappeared because there is no surface anymore. Okay. So that's kind of the scenarios with force, with apparent weight. So I've got one example for you. In this example, we have a situation where a person has a mass of 68 kilograms. They're descending meaning they are moving down in an elevator at a constant velocity of 4.0 meters per second. Now, constant velocity, remember, this tells us that the person must be moving at a uniform rate, which means their acceleration is 0 meters per second. Now, at some point, as they're getting to the floor that they're wanting to stop at some point the elevator starts to slow down. And it starts to slow down at a rate of 2 meters per second squared. Okay, so that's kind of the setup. So at some point, after they've been traveling at a uniform rate, they're going to start decelerating, right, in order for the elevator to slow down. So what we want to know is if the person in the elevator were standing on a bathroom scale, and it's calibrated to newtons, so it reads weight, what would the scale read while the elevator is A, descending at a constant speed, and B, slowing down to a stop? So for A, when they're descending at a constant rate, that means that they're moving at uniform motion, or acceleration is equal to 0. So that means that if we draw our free body diagram, we know that we're descending. So I'm going to say down is positive. Force gravity, if we're moving at a constant rate, force gravity is balanced with force normal so that our net force is 0. And in this case, if we set up our equation, we'll say net force is equal to the sum of the forces, which means that net force is equal to our force normal plus our force gravity. And we don't have an actual force gravity, we've been given a mass. So we have to expand this to say force net is equal to force normal plus mass times gravity. And now we'll plug in our numbers. So we know that we're moving at a constant rate. So we know our acceleration is 0, which means that our net force is 0. Force normal, we don't know. We know our mass, and we know that our acceleration is 9.81 meters per second down. And we've set down as positive, so I'm keeping that as positive. And if I solve for force normal, I get that normal force is 667.08 newtons negative, or 6.7 times 10 to the 2 newtons up. Now, in terms of my apparent weight, this number just is a representation of the apparent weight. It doesn't tell me that my apparent weight is in the upward direction. My weight is always, pulling me down. So for this, the person's apparent weight, because we're moving at a constant rate, their apparent weight is going to be equal to their true weight. Remember this diagram that we had up here? When acceleration is 0, the apparent weight is going to equal to the true weight because the force normal is equal to the force gravity. So that means that if the person's force normal is 6.7 times 10 to the 2 newtons, that means that their true weight, or their apparent weight, is going to equal their true weight, and their apparent weight is going to equal 6.7 times 10 to the 2 newtons. Okay. Now, the second scenario is, well, what happens if the person is it decelerating? Their acceleration is 2.0 meters per second in the upward direction. So that means that if they're decelerating, that means that for an instant, their inertia is going to want to keep them moving in the downward direction. But all of a sudden, they're going to start slowing down, right? The elevator is going to start almost appearing to move up into them because it's slowing down, and the person is still accelerating at the original rate, or is still traveling at the original velocity. So that means that what's going to happen here is that their force normal is going to get really large in comparison to their force gravity. So maybe I'll make this a little bit smaller so that you can really see that properly. Right, so their force normal will get really, really large because the elevator floor is going to start slowing down, and then the person is going to move into the scale because they're traveling quicker than the elevator for an instant. So if we set up our system of equations here, we have our force net is equal to the sum of the forces. So our force net is equal to the force gravity times the force normal. Because we are accelerating, we have to expand F net to be mass times acceleration. We're still looking for that force normal, and we're looking for force gravity, which is mass times gravity. So if I plug all of these numbers in, I know that the mass of my person is 68 kilograms. The acceleration is 2.0 meters per second, and I've said that down is positive because that's the direction of the elevator. So that means my acceleration will be negative. And that's equal to force normal plus 68 kilograms times 9.81 meters per second squared, positive because down is positive. And so that means that my force normal is 803 newtons up. Well, what that tells me is that for this particular person, therefore, their apparent weight will appear to increase to 8.0 times 10 to the 2 newtons. That's what it'll appear to be. So it'll appear like they're getting heavier. Okay, so those are apparent weight questions, guys. And we'll spend some time in class practicing these. I have a worksheet for you guys all about elevator problems. So if you've got questions, let me know. We'll do some practice problems together as a group when we see each other next time. But as always, I do hope you're doing well. And let me know if there's any questions. Take care.